So we want to start with section 3.3, which covers differentiation rules. And up to this point, we've been using the limit definition, which is the definition, but it is tedious and it is long. All right, when you do the f of x plus h minus f of x all divided by h, then take the limit as h goes to 0. These are very long processes to find the limit value at a particular point or the limit value as a function, the derivative. There are shorter methods of finding these, and that's what we're going to do today. Once we find these rules today, these will be the rules that you'll use almost all the time, 99% of the time. It will be rare that you'll go back to using the limit definition, but we start with the limit definition so that you really understand where it comes from and what the meaning of it is. And then we give you the shorter versions of them. So we're going to start with the constant, multiple, and power rules. Then we'll talk about sum and difference rules. We'll do the product rule and the quotient rule. And then we'll talk about the power rule for negative exponents. And then we'll put all of it together to do all the different rules in one combined thing. All right. So the basic differentiation rules are the building blocks of finding the derivatives are constant c and power terms x to the n. So we start with these basic types of functions, and then we build the rest of the rules from them. So we're going to start with the geometric understanding, and then we'll go algebraically, which is what we've been doing most of the semester. Remember that when you have a horizontal line, it has the equation of y equals c. So that's a horizontal line. This one happens to be, I think, y equal 1.5, looks like right there, all right? And that's just a horizontal line. Now, if I asked you, what is the slope of the derivative? You would say, well, what is the slope of a horizontal line? Well, it's 0, right? There's no vertical change. There is horizontal change. So the slope of a horizontal line is 0. So the derivative must be 0 everywhere, all right? So if I were to graph the derivative of this function, I would be graphing basically, oops, I'm in the wrong spot. I would be graphing the x-axis, all right? Picked the wrong line. Okay. So if we're looking algebraically, then we can use the limit definition. And remember that f of x plus h, since it's a constant function, would still give us the constant. And f of x would still be the constant. So we have the constant minus the constant, which is 0 over h, which is the limit of 0. There's no place to plug in the h because we've already decided 0 divided by h is 0. So the limit is 0, all right? Notice that we got rid of the h before we evaluated the limit, and that's what avoided that 0 over 0 indeterminate result. So the first theorem is the constant rule for differentiation, which is if you have a constant function, the derivative is 0. And this is the more common way of writing it. The derivative with respect to x of c equals 0. And that's how you read it, the derivative with respect to x. So let's write that down in words. All right, so the derivative with respect to x of a constant is 0. All right. So find the derivative of g of x equal to -3. So if you take the derivative with respect to x of g of x, you're going to get 0 because it's a constant. All right. So it's always going to give you 0. Okay. It doesn't matter what the constant is. If I gave you the derivative with respect to x of pi, it's still a constant. You should give me 0. All right. Even if I said, what's the derivative with respect to x of 0, it's still 0. 0 is still a horizontal line. It's the x-axis, but the slope of that horizontal line is 0. All right. Now we want to talk about the derivative of a power term, or the power rule, which is if you have something that looks like x to the n. So if you have something that looks like x raised to a power, the power rule is kind of weird, but you'll get very used to it because you're going to use it hundreds of times between now and the end of the semester. You pull the power to the front, and then you reduce the power by 1. So the derivative of x to the nth power is n times x to the n minus 1. All right. So the derivative of x to the n is n times x to the n minus 1. Pull the original power to the front, reduce the power by 1. So let's say that I gave you something that looks like the derivative with respect to x of x to the 5th power. Pull the 5 to the front, then write the variable, reduce the power by 1, so you get 5x to the 4th. All right. Okay. Now the proof of the power rule comes from using the binomial theorem, and the coefficients on the binomial theorem are approximated with, or not approximated, they're found by using n factorial over k factorial times n minus k factorial. And this is something that we call n choose k, that you will see again in calculus 2. Now, how many of you know what a factorial is? Or how many of you do not know what a factorial is? Okay, so let's talk about what a factorial is. If you have something like 5 factorial, this just means take 5 and multiply by all of the integers until you get to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. So if we had something like n choose k, then we would write it like this. So if we had 5 choose 2, we would write 5 factorial over 2 factorial times 5 minus 2 factorial, which gives us 5 times 4 times 3 times 2 times 1 over 2 times 1 times 3 times 2 times 1. Now the 3 times 2 times 1 cancels that 3 times 2 times 1, and the 2 will go into the 4 2 times, and you would end up with 10. It's a way of generating the coefficients. Now, you can also generate the coefficients with Pascal's triangle. There's another name for it as well, and I can't come up with it right now. It's a famous Chinese triangle as well. It's not coming to me. But at any rate, they've had it as well, longer than Pascal came up with it. So Pascal's triangle is another way of developing these coefficients. All right. So these become the coefficients of a binomial when you multiply a binomial by itself a certain number of times. So Pascal's triangle, if you've never seen it, starts with a 1, then a 1, then a 1, then a 1, then you add those two together and then you get a 1, then a 1, then a 3, then a 3, then a 1, then a 1, then a 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So what I'm doing is I'm adding together the two numbers, and that gives me the number in between on the row below. So the first number is always a 1. The last number is always a 1. And to get the 2, I add 1 and 1 together. 1 plus 2 gives me 3. 2 plus 1 gives me 3. 1 plus 3 gives me 4. 3 plus 3 is 6. 3 plus 1 is 4. It always ends with a 1. Always starts with a 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. It always ends with a 1. All right. So this is the triangle that I was talking about. and it generates the coefficients of multiplying a binomial by itself. So what do I mean by a binomial by itself? If you take a plus b and you raise it to the first power, your coefficients are 1a and 1b, right? What if you take a plus b and you raise it to the second power? Your coefficients will be a squared plus 2ab plus b squared. Coefficients would be 1, 2, 1. Does everybody see that? If you took a plus b and you cubed it, your coefficients are going to be a cubed, 1a cubed, plus 3a squared b, plus 3ab squared, plus b cubed. That's the way the triangle works. So it generates those coefficients. So when we say 5 choose 2, we're talking about this coefficient right here, where we always start counting. Instead of with 1, we start counting with 0. So this is the 0th, 1st, 2nd. So this is in row 5, 1, 2, 3, 4, 5. And it's the second item when you're counting starting with 0. So 0, 1, 2. So 5 choose 2 gave me that 10 value right there. So this formula that you see right here, written as 5 choose 2, is a way of generating the coefficients that come up in the triangle, which are the same coefficients that come up as the coefficients of a binomial multiplied by itself. Now that's what we need, because we want to prove that in general, the proof is x to the n, the derivative is nx to the n minus 1. And when we apply our definition for the limit for the derivative, we have this f of x plus h. And because we have f of x plus h, we have x plus h raised to the nth power. So we need the triangle, or the 5 choose 2, in order to generate the coefficients that are going to show up in front of it. So the next line down here, what you see here is x to the n, nx to the n minus 1. This would be the next coefficient coming across on each one. All right. So it's basically generating the coefficients for each term as you go along according to the triangle. All right. But we're using a generic n instead of a particular number. All right. Now, the next thing we're going to do, of course, is we have to subtract the x to the n term. So again, what we're doing is we're using this formula up here, f of x plus h, which is x plus h to the nth power, minus f of x, which is minus x to the n. So first we expand the binomial using the binomial theorem to generate the coefficients. And then we subtract the x to the n, which is going to take off this first term right here. All right. And it's going to leave the subsequent terms after it. So you see those right there. Then we're going to divide everything by h and reduce it. So we divided all the terms by h right here in this term. And then we reduce it by 1 to get 1h to get the next line. Finally, you apply the limit as h goes to 0. Now, as h goes to 0, all the terms that still have h in them are going to go to 0. So all of these back here that still have h's in them get multiplied by 0. So they disappear, and we're left with just the first one, n times x to the n minus 1, which is the proof. And you'll see that it ends there with QED. All right. Now, the application of it is super simple compared to the proof of it. The proof required the binomial theorem. But to apply it, I would say f prime of x is pull the original power to the front, write the variable, subtract 1 from the original power. So I get 7 times x to the 6th power. All right. That's the power rule. And like I said, you'll be using this rule hundreds of times. by the end of the semester. By the time you get into Cal 3, it will be thousands of times. You'll be using this rule so often, it will become instinctive for you. Now we're going to talk about the sum, the difference, and the constant multiple rules for differentiation. We'll start with the sum rule. Now we had these rules for limits as well. And remember, when we had the limit of a sum, it became the sum of the limits. So you might not be surprised to see that the derivative of a sum is the sum of the derivatives. And this will also work for the difference. So the sum and difference rule, the derivative of a sum is the sum of the derivatives, and the derivative of a difference is the difference of the derivatives. However, it does not work for multiplication and division. The limit of a product is the product of the limits, but that is not true for the derivative, and neither is it for the quotient. So you have to be careful not to apply the rules too far. You can do more with the limit form than you can with the derivative form. So if we have a function h of x, which consists of two functions added together, f of x plus g of x, and we want to take the derivative of h, we just take the derivative of each term individually. So what does that let me do? Well, if I have h of x is equal to x to the fourth minus 2x, then this is going to let me take the derivative of each term individually. So when I take the derivative, I'll take the derivative of x to the fourth, bring the 4 to the front, reduce the power by 1 to 3. Now, what about on the minus 2x? This is kind of a tricky rule. This gets back to your algebra. The power on x is not written, but it's understood to be 1, right? So we bring the 1 to the front, multiply it by the 2, so I get a 2. But when I reduce the power, it has to reduce to 0. What is x to the 0th power equal to? Anybody remember?
1.
Yes, just 1. Good. So it is just 1. So it becomes 4x cubed minus 2. All right. So the derivative of the sum is the sum of the individual derivatives. All right. And we'll go through the proof rather quickly. So when we're looking at this particular one, we probably won't go through all the proofs today, but we'll go through this one. When we're looking at this one, we're going to let J be f of x plus g of x. And so J is a combined function of two other functions added together. So we want to apply the limit as h goes to 0 of the difference quotient, which is j of x plus h minus j of x all divided by h. So this is going to give me j of x plus h, which by definition of what j is f of x plus h plus g of x plus h. So I'm going to plug those into the difference quotient. So I have f of x plus h plus g of x plus h minus j of x, which is f of x plus g of x. That's just using the definition of what j is. Then we rearrange the terms and regroup them so that I'm going to take the f of x plus h here with the minus f of x and the g of x plus h here with the minus g of x. And you can see that what I'm building, of course, is two separate difference quotients, one for f and one for g. Now the limit of a sum is the sum of the limits, so I'm allowed to split this up into two different ones. And this by definition is the derivative of f, and this by definition is the derivative of g. So I have f prime of x plus g prime of x. Questions about the proof? The proof was pretty fast. It's mostly a matter of rearranging the terms. No questions? Okay. The difference rule is the same as the sum rules, just with subtraction. If you have a function defined to be the difference of two functions, then to find the derivative of the original, you take the difference of the individual derivatives. All right. And we won't go through that proof. It's essentially the same. You just have to rearrange the terms. And then we have the constant multiple rule. We had a constant multiple rule for limits as well, and it said that you could pull the constant multiple out of the limit. And we have the same rule here. If you have a constant being multiplied by a function, then you can pull the constant out and then do the derivative. So let's say that I had f of x equal to 4x to the 7th minus 8x squared plus 12. I could pull the 4 out first. If I want to do f prime, I could say instead that I'm going to pull the 4 out and then do the derivative on the x to the 7th minus 2x squared plus 3, all right? Which would give me 4 times 7x to the 6th minus 4x to the 1st plus 0. Remember, the derivative of a constant is 0, which would give me 28x to the 6th minus 16x, which is the same thing I would have gotten if I had done the derivative directly. All right. If I'd done the derivative directly from the beginning, I would have gotten the same result. Okay. There are occasions when we want to pull out the constant. On those occasions, we typically would leave the constant pulled out. We wouldn't put it back in. I mean, there's not much reason to pull it out and then put it back in. If we pull it out, it's usually because we're going to factor. So we would pull it out and then we would leave it in a factored form so we could factor it further. Okay. So let's apply this to a couple of examples. We have example 3. So take a minute here and go ahead and find the derivative on example 3 and example 4. So I'll give you a minute to do those. Okay, so the derivative on example 3, you should have brought the 3 to the front to multiply by the 2, which gives you 6. Reduce the power by 1 to become a 2. Minus 2 brought to the front multiplied by the 6 will give me a 12. Reduces the power to 1. You can write the 1 or not write the 1. Either way is correct. And the derivative of 3 is 0. So I would have had 6x squared minus 12x. And on number 4, I would have f prime would be bring the 3 to the front to multiply by the 5, which would give me 15. Reduce the power by 1 to x squared. Then what about the derivative of the x? Remember that the x is x to the first. So you get a 1 times 1. And then you have an x to the 0 plus 0, because a derivative of 1 is a constant, so it goes to 0. And remember that x to the 0 is just the number 1. So you can write this as 15x squared minus 1. Basically, what we're saying is the derivative of x is 1. All right. It is the power rule. You are pulling the power 1 to the front, reducing the power by 1 to become the 0th power. X to the 0 is 1. So the derivative of x is 1. All right. It is the power rule. It does work. But most students eventually just memorize that the derivative of x is 1. All right. What about examples 5 and 6? We'll start with 5. The derivative here would give you what? It should give you 32x cubed plus 18x. Pull the 4 to the front to multiply by 8 to get 32. Reduce the power by 1 to get 3. Pull the 2 to the front to multiply by 9 to get 18. Reduce the power by 1 to get x. The derivative of a constant is 0. So the derivative of 1 doesn't add anything to the derivative. Now, what are we finding when we do this? Believe it or not, we are finding the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. In other words, if we were to take this function right here and we were to work out 8 times x plus h to the 4th plus 9 times x plus h squared plus 1 minus 8x to the 4th plus 9x squared plus 1 in parentheses, and divide all of it by h, then some 10 minutes later, we would come up with 32x cubed plus 18x, right? But it would probably take us another 10 minutes to do one like this. It's quite complicated when you have to multiply by itself 4 times, right? It would become algebraically difficult. But the short rule gives us the answer very quickly, right? Let's take a look now at example 6. It says, find the equation of the line tangent to the graph of 3x squared minus 11 at x equal 2. And then we want to use the point slope form to find the tangent. Then we're going to graph the function and the tangent line on the same graph. So the first thing we need to do is we need to find the derivative function. So to find the derivative function, I take the derivative of the function. The 2 comes to the front to multiply by the 3 gives me a 6, reduce the power by 1. The derivative of negative 11 is 0. So this is the derivative function. And then I want to find the derivative at a particular point. So then I find f prime of 2, which gives me 6 times 2, which is 12. And this will give me the derivative at a specific point. All right. So this is when we use that limit as x approaches a of f of x minus f of a over x minus a form. If we use that form, we end up with the derivative at a particular point. So this is replacing this process right here. So now we know that the slope of the tangent line at that point is 12, but I don't know what the point is. I know it's at x equal 2, but I don't know what the y value is. So I need the y value at the point by plugging it into the original function. So this would be f of 2, which is equal to 3 times 2 squared minus 11, which is 3 times 4 minus 11, which is 1. So this gives me the ordered pair 2, 1. So then I write the equation in point slope, y minus 1 equals my slope of 12, x minus 2, right? And then we said we wanted to graph it. So we have 3x squared minus 11. So I've got Desmos on here somewhere from yesterday, I think. So let's get rid of all these. So my original function was 3x squared minus 11. And my equation was y minus 1 equal 12, x minus 2. All right. So do you see that it is tangent at that point right there? If I can find it right there at 2, 1. The line is barely skimming along the surface of this parabola and barely touching it at that one point. So it's tangent to it. I always kind of think of it as being like a yardstick on a big ball, right? You take a yardstick and you balance it on a ball, it's just going to touch at one single point. And that's what we're talking about for being tangent, touching at that one single point. All right. Okay. So if you want to take a picture of this, I thought I had my snippet open, but I must have closed it. So there's our tangent. And we can add that to our notes, right? Now the product rule is much more complicated than the rules that we've done so far. The product rule for derivatives is not the derivative or the product of derivatives. It does not work that way. It only works for the sum and the difference. That's it, those two. And later this semester, we're going to learn about integration. And when we get to integration, we're going to have exactly the same situation. It will work for the sum. It will work for the difference. It will not work for multiplication. It will not work for division. You cannot split a derivative and take the derivative of each part and then multiply the derivatives together. It won't work. The rule instead is right here. So the rule is rather complicated, all right? To take the derivative of a product, and a product means they're multiplied together, then it ends up being the derivative of the first term times the second term unchanged, plus the derivative of the second term times the first term unchanged. Now, we sometimes write this in a different format, which looks like this right here, all right? So sometimes we write it as f prime g plus g prime f, all right? So when you have to take the derivative of a product, you have to apply the formula f prime g plus g prime f. Derivative of the first times the second plus derivative of the second times the first, right? Let's see why this is true. So we'll go through this particular proof. All right, we're going to start with a function j. J is going to be the product of f and g. And we're going to use the limit as h goes to 0 of the difference quotient again, since that is the formal definition of the derivative. So j of x plus h minus j of x. J by definition is f times g. So we get f of x plus h times g of x plus h to replace j of x plus h. Minus j of x becomes minus f times g. Now we have to do a technique or a trick. We call it a trick. It's really a technique of adding 0 by adding and subtracting the same term. And what we want to add and subtract is f of x times g of x plus h. So we subtract it and we add it in the middle. By subtracting and adding the same term, we're effectively adding nothing. We call this adding 0, right? What it's going to do is it's going to allow me to split this into two different limits, all right? And then I'll have a common factor in each one. So the next line down, I split the quotient into two parts where I take the minus f of x, g of x plus h with the first part here, and I take the plus f of x, g of x plus h with the second part here. So I just split it into two different quotients. Now, these are not the difference quotient, but they are quotients, right? They're ratios of things. This first one now has a common factor of g of x plus h, and the second one has a common factor of f of x. Does everybody see that they both have each of those factors? So the next step is we're going to factor the common factor out of each of those terms. So we take the g of x plus h out of the first part, and then you can see that this part right here is a difference quotient. It's f of x plus h minus f of x over h. When you factor the f of x off the second half, you'll see that this part is the difference quotient, g of x plus h minus g of x over h. So this is what gives rise to the formula then we split the limit among the product, because you're allowed to do that with limits. You're not allowed with derivatives or integrals, but you're allowed with limits to split products into limits of products or limits of factors. So we have the limit of the first factor, which gives us f prime. G of x plus h, the h is going to go to 0, and we just get g of x. The limit of the difference quotient is g prime. F of x doesn't depend on h, so the limit just becomes f of x. So that by the definition of the derivative, this gives us our terms f prime g plus g prime f. All right. So this is a formula that you have to memorize. There's really no other way around it. And it's certainly not an easy one to derive. So you're just going to have to memorize it. I'm going to show you two methods on this problem here of attacking it, and then talk about why you wouldn't always use two methods. So we'll do method 1, which is the quotient or product rule. Getting ahead of myself. So we're going to use the product rule. My advice is every time you apply the product rule, write down the rule, f prime g plus g prime f. If you write the rule every time you use it, by the end of the homework, it will be memorized. All right, that's the most effective way. So what I need is the derivative of 2x to the 5th multiplied by 4x squared plus x. And then I'm going to add on to that the derivative of the second, which is 4x squared plus x. And then I'm going to multiply by 2x to the 5th. So I'm taking the derivative of the first factor, multiply it by the second factor, take the derivative of the second factor, multiply it by the first factor. All right. So this is f prime, derivative of the first factor, then multiply by the second, then derivative of the second, multiplied by the first. Now, I would probably not write that step. I would go straight to applying it. So the derivative of 2x to the 5th is going to be 10x. Then I multiply by 4x squared plus x. And then the derivative of 4x squared plus x using the sum rule would give me 8x plus 1. And then I would multiply that by 2x to the 5th. And I'm going to probably need more space. All right. Now, if I want to multiply this out, this would give me 40x cubed plus 10x squared. Over here, multiplying and distributing from the back would give me plus 16x to the 5th plus 6. Oops, maybe I should just erase that. 16x to the 6th plus 2x to the 5th. And if I rearrange it and put it in descending order, I get this. All right, which works okay for binomials. All right, what is method 2? And then we'll talk about why we might not do method 2.
Wait, I have a question on the last one.
Did I mess up?
Wouldn't the 10x at the start be to the power of 4?
10x. Yes. Oh, thank you. I missed it. All right, 10x to the 4th. Yes, so that changes everything. That would make this 40x to the 6th plus 10x to the 5th. So now we've got, going too fast. We've got 56x to the 6th, good catch, plus 12x to the 5th. Okay. We'll know in a second whether or not we've got it right because method 2 should match. All right, did I do that right now? 10x to the 4th, 8x plus 1. Okay, so check my algebra again, make sure I got that right. That's your job, is to check the algebra. Method 2 is just to multiply out first. All right, so I'm going to rewrite j of x as 8x to the 7th. When the bases are the same, you add the powers. So 5 plus 2 gives us 7, plus 2x to the 6th. All right, and then I can take the derivative from this form. J prime of x would be 56x to the 6th plus 12x to the 5th. Now, which one was faster, shorter, and easier? Method 2. So if method 2 is shorter, faster, and easier, why do we even bother with the product rule? A couple of reasons. What if your function h of x was equal to 2x plus 1 to the 5th power times 3x plus 2 to the 3rd power? Multiplying that out would not be trivial. It would take quite a long time. All right. We're going to learn a technique called the chain rule that will let us multiply and find the derivative of this one much more easily. We could also have a mixture of types of functions. We could have 2x squared plus 3x plus 5 times the sine of 2x. Then we would also have a problem. How do we do that given that they're not even the same type of function? They're not both polynomials, all right? So we need the product rule for occasions when we wouldn't want to multiply them out directly, or when, because they're different types of functions, we couldn't multiply them out, all right? So the product rule is for situations where it would be too difficult to multiply out, or it would be impossible, all right? Okay, let's try it on another one, and we'll do both methods again, since this is a polynomial times a polynomial. Uh-oh. Okay. It's kind of messing up on me, I can tell. All right, so we've got j of x is equal to f, oh, there it went. I knew that was going to happen. All right, hang on while I close it and reopen it. Save. Pick up where I left off. All right. Okay, so this is f, which is x plus 2, and g is going to be our 2x squared minus 3. So we're going to do method 1, which is the product rule. So j prime of x is equal to f prime g plus g prime f, which is going to give us the derivative with respect to x of x plus 2 times 2x squared minus 3 plus the derivative with respect to x of 2x squared minus 3 times x plus 2. The derivative of x plus 2 is 1, so we just have 1 times 2x squared minus 3, plus the derivative of 2x squared minus 3 would be 4x times x plus 2, which would give us 2x squared minus 3 plus 4x squared plus 8x, which would finally give us 6x squared plus 8x minus 3, right? So that's what I get from using the product rule. what would I have gotten if I just multiplied it out? All right. And because it is two polynomials with not very high powers on them, I can multiply it out. So using the rules for the distributive property, I get 2x squared times x gives me 2x cubed. On the inside, I have plus 4x squared. On the outside, I have a minus 3x. And for the last, I have a minus 6, right? So I got 2x cubed plus 4x squared minus 3x minus 6. Then when I take the derivative, I can do it directly using the sum and difference rules. And I get 6x squared plus 8x minus 3. Remember, the derivative of a constant is 0. All right, I get the same result. Now we want to talk about the quotient rule. The quotient rule is the most complicated one of all the rules. It is more complicated than the product rule, although it's similar. It's f prime g minus g prime f all over g squared. I suggest you find your own pattern and your own rhythm to saying it. Some people who can sing, there is a song you can Google and you can say it. Google the quotient rule and song. I can't sing, so I am not going to sing it for you. It would not help you any, I can promise you that. But you can use a different patterns for getting it. But whatever pattern you choose, use the same pattern every single time, and it will stick with you as you practice it. It does take a lot of practice. But I have found that because I always in my head say it the same way, and in fact, sometimes mutter it under my breath, that it comes out even now, some 4 decades after I learned it, the exact same way as it did when I learned it. So I learned it as the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That's what I memorized, and it stuck with me. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. You in your textbook tends to follow the f prime rule. So it does f prime g minus g prime f over g squared. Notice that the numerator is almost the same as the product rule, but with a minus in the middle, and it's divided by g squared. All right, so this is the quotient rule. Almost the same as the product rule, but with a minus, and it's divided by g squared. We are not going to go through the proof. The proof is similar to the product rule, but it does take quite a bit longer, so we're going to leave it off. So when you're talking about the quotient rule and doing the derivative, could you do it a different way? Well, yes, technically you could use long division. But if you use long division, I don't think long division is easier than the quotient rule. So I don't see any advantage to it. So I don't ever teach it that way. So what we're going to do now is we're going to think of this as f and this is g. And we're going to do, I've got to remember to do it the way you guys do it. F prime g minus g prime f over g squared. Okay. All right, so we're going to take the derivative of the top times the bottom minus the derivative of the bottom times the top, or numerator, all divided by the denominator squared. Now, most of the time we skip that step right there. It won't hurt you to write it out the first few times as you're learning it, but most of the time, honestly, we skip that step right there and we go straight to the next part, which is taking the derivative. So the derivative of 3x plus 1 is 3. And then we multiply it by the denominator, 4x minus 3. Then we take the derivative of the denominator, which is 4, and we multiply it by the numerator, which is 3x plus 1. And then we divide it by the denominator squared. We do multiply out and reduce the numerator. We typically do not multiply out the denominator. We typically leave the denominator squared, since if we need to factor it, it's already in factored form. But the numerator is not because of the subtraction in the middle. So we typically will go ahead and multiply that out. There's often some cancellation that occurs, but not everything will cancel and disappear. All right. Notice that we do get the 12x's to disappear, but then we're left with -9 minus 4, which gives us a -13 over 4x minus 3 quantity squared. That is what we are looking for. All right. Now, what is that? That is the derivative function for this particular function here, 3x plus 1 over 4x minus 3. And I got my y in the wrong place, didn't I? There we go. So there's my function, 3x plus 1 over 4x minus 3. And let's say that we want to know what the slope is at a particular point. So let's find a point on the graph. Looks like 1, 4 is on the graph. So I want to find the slope at 1. All right. So if I come over here and I want to take the point 1, 4 and find the tangent line, then I'm going to take the 1 and I'm going to plug it into the derivative function formula, which is right here. 4 times 1 would give me 4, minus 3 would give me a 1. 1 squared is 1, so the slope is a -13. So this is going to give me the equation of the tangent line, y minus 4 equal -13, x minus 1. Does everybody see that it is in fact tangent at that point? So what we're getting when we get the derivative is we're getting a function which represents the derivative value at any point. And then I can find a point on the graph and I can find the slope of the tangent line there. And I can write the equation of the tangent line by using the point slope form of the line. All right. Okay. I think a lot of ice just slid off my roof. Okay, let's try another one. This is example 10. So I'll give you guys a minute and I'll take a minute. We'll both work them and then we can compare our answers. All right, so take a moment and go ahead and work it out. Remember the formula, which is f prime g minus g prime f over g squared. And this time you don't have to write it out formally. I will, but you don't have to. Okay, compare your answer to mine and see if they match up. All right, remember that we're getting the derivative function, not the derivative at a particular point, but the derivative at any point x. We go to the graph, we find a point on the graph, we can plug the x coordinate in, that will tell us the slope of the tangent line there, and then we can find the equation of the tangent line. Okay, let's practice it another time. This one is a little bit different in that we have a mixture of a first degree polynomial with a second degree polynomial. So our denominator is more complicated. So go ahead and take a moment and write this one out. Okay, so hopefully you got the same thing that I got right here. Notice that one of the things that I did, I left enough space here so that I could distribute the negative through the entire thing. And also notice I did not distribute the negative until after I had combined the two binomials. I know myself, I know where I'm likely to make a sign error, and that's where it is. So I even still, after years of doing algebra, I know it's faster in the long run just to not make the error by not trying to do too much at once. So I multiply the binomials together first, then I change the sign above it. It makes it much simpler to do, and in the long run, it's faster, all right? And I would leave it in the factored form for the denominator. I doubt that the numerator factors. It's possible, but I doubt it. The denominator, however, definitely does not factor. With a +1 here and a 7x in the middle, that quadratic's got to be prime. Okay. All right. Let's take a look at example 12. We want to find the equation of the tangent line to the graph of the function at the point -1, 1. Then we'll graph both using technology. So this is similar to the one we did a minute ago. So we have 2x over x minus 1. The numerator is our f, the denominator is our g. So we're going to be looking for h prime of x, which is going to be f prime g minus g prime f over g squared. And this time, I will not write out the derivatives. I'll do it directly. So the derivative of the numerator is a 2, and then you multiply by the denominator, which is x minus 1, minus the derivative of the denominator is 1, multiplied by the numerator, which is 2x. Again, don't do too much at one step, or you will make a careless mistake. And then we divide by x minus 1 quantity squared. All right. Once we have that, we can simplify 2x minus 2 minus 2x over x minus 1 quantity squared, which gives us -2 over x minus 1 quantity squared. We're at the point -1, 1. So we're going to plug in x equal -1. So we get h prime of -1, which is equal to -2 over -1 minus 1 squared, which is going to give me -2 over -2 squared, which is 4. So I get a -1/2. All right. Once I have -1/2, I can write the equation of the tangent line. And the equation of the tangent line is going to be y minus 1 coming from here equal to -1/2. This is the slope of the tangent line times x minus a -1, which makes it x plus 1. All right. Let me come and put that over here. So my function is 2x over x minus 1. And my equation is y minus 1. My slope is a -1/2, which I can write as 0.5 x plus 1. All right. And there it is right there. Right. And you can see that it's tangent right there at the point -1, 1. And I can take a photograph of it and then paste it into my work. Okay. Now, everything that we're learning today, you're not allowed to use on the first exam. The first exam is nothing but the difference quotient, which is why I cut it after 3.2. So you're not allowed to use any of these rules on the exam, except, can I stop you from checking your work with these rules? No, I cannot. So you can check your work and then you'll know whether or not you got the difference quotient problem right, because you know what the answer should be. Okay, we're going to do the power rule for differentiation. And in fact, I'm going to give you the full power rule. The textbook does it one step at a time. First, it does it with positive exponents, then negative exponents, then rational exponents. And somewhere in the book, it finally just says, okay, it works for all reals. I'm just going to tell you right now, it works for all reals. All right. The proof of it, however, is very advanced and far beyond the scope of this course. It's beyond even what the Calculus 3 students would be doing, okay? So it's a very difficult proof, so we're not going to go through the proofs, but basically this power rule where you pull the power to the front and reduce the power by 1, it works for all real numbers, which means if I have something like x to the pi, this is pi x to the pi minus 1, all right, where pi minus 1 would be about 2.141569, blah, 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 all right? So again, it does work for all values, including negatives, rationals, and irrationals, all right? It works for all of them. The proof for negatives is here in the notes. I'm not going to go through it. We're just going to use it in our mixed practice, all right? So this is where we have slightly different problems. The first one starts with find the values of x for which the graph of 4x squared minus 3x plus 2 has a tangent line parallel to the graph of y equal 2x plus 3. So you have to use the rules for parallel lines. And that basically is that parallel lines have the same slope. All right, parallel lines have the same slope. So M parallel is going to have to be equal to 2 because the slope of this line, since it's in slope-intercept form, is 2. Remember, slope-intercept form is y equal mx plus b, all right? So this is definitely 2x plus 3, so the slope is 2. So we want our slope to be 2. Well, first we need a formula for our slope, and the formula for our slope is the derivative of the function. So then we get 8x minus 3. So basically, we want to look for x values where those are equal. So where is 8x minus 3 equal to 2? That's a really bad 2. There's a better 2. All right. I grant you my 2s are not great, but I do the best I can. My printing is not the greatest. I should have been left-handed, but when I was a child, nobody was left-handed. And so they forced me to write with my right hand, but I do everything else left-handed. So, so my handwriting is not very good. Sorry about that. I'd even mouse with my left hand. I wear my watch on my right hand. Yeah, I do everything backwards except right. Okay, so we can solve this by moving the 3 to the other side and then dividing by 8. So we end up with x equals 5/8. So we're basically looking at the point 5/8. So we need to find the point on the graph where x is 5/8. So we're going to plug this into our function, and that will give us the point where x is 5/8. So our function again was, copy that off. I think I copied it. Paste it down here. So I'm looking for f of 5/8, which is going to be 4 times 5/8 quantity squared minus 3 times 5/8 plus 2. All right. So work out the algebra. I got 27/16. Check and see if you agree with that. 5/8 is 64. 25/64. 4 goes into 64 16 times. So you get 25/16. And then this becomes minus 15/16. And then you can write 2 as plus 32/16. All right. And I believe that gives you 27. Did I do that right? 3 times. Oh, no, this is 15/8, which would be 30/16. There we go. That works better. Okay. All right. So now we have our ordered pair, which is going to be 5/8, comma, 27/16. So we can take the equation 4x squared minus 3x plus 2. And our equation was y minus, was it 27/16? Yeah. Yes. And my x was 5/8 minus 5 divided by 8. And I believe my slope was a 2, was it not? I wanted the same slope as on that line. And there's the point right there. All right. 5/8 is 0.625. So I know I've clicked on the right spot there. And then we can take a picture of it and add it to our notes. Okay. The next thing that we want to do is just find the derivative using the quotient rule and then simplify the expression first and find the derivative again and decide whether we get the same results, why or why not. So our function here is really, and maybe instead of calling it f, I should call it h so that we can use f and g for the formula. 4x cubed minus 2x plus 1, all divided by x squared. All right. So we're going to do h prime of x using the quotient rule. So the quotient rule is f prime g minus g prime f over g squared. So the derivative of the numerator is going to give me a 12x squared minus 2 in parentheses times g, which is x squared, minus the derivative of the denominator is 2x in parentheses times the numerator, 4x cubed minus 2x squared plus 1, all divided by the denominator squared. Now, if you've left enough space, you can work above it and distribute some of this out. So x squared times 12x squared and x squared times -2, that will give me a, what will that give me? I want a little bit more space. Let's see if I can scooch it down just a little. So that gives me 12x to the 4th minus 2x squared. And then I have a minus, and then I have parentheses around the whole thing. And then this is going to give me 2x times 4x cubed would give me 8x to the 4th. And then the next one would give me minus 4x cubed. And then the next one give me plus 2x. And then I could further work some of this out. Oops, that didn't work. Right. By going ahead and distributing it and writing minus 8x to the fourth plus 4x cubed minus 2x. If I leave enough space, I barely have enough space, but I think I've got enough. All right. So make sure that you distribute correctly. My advice is to double check the distribution before going on, because if you make a mistake, it's usually in that second term after the subtraction, either in the distribution or in the distribution of the negative. So check both to make sure that you've got it correct before proceeding. And once you get to that point, then you can combine your like terms, and h of x turns out to be, let's see, I've got 12x to the fourth minus 8x to the fourth, which gives me 4x to the fourth. And then I've got, did I mess up on something? I did. I copied wrong. This isn't a square. This is 4x cubed minus 2x plus 1. And I copied it wrong. Okay, I thought something looked off. All right, so this would be minus 4x squared. And this would be plus 4x squared. Anybody else see an error in there? Now it looks correct. Okay, so I've got 4x to the fourth minus 2x squared plus 4x squared gives me a plus 2x squared. Oops, still using the wrong color. And then I've got minus 2x. And it's all divided by x to the fourth. All right. Now, if I wanted to, I could reduce this, since I have a single term polynomial in the denominator with no addition or subtraction. I could split this into 3 fractions and write it as 4x to the fourth over x to the fourth plus 2x squared over x to the fourth minus 2x over x to the fourth if I wanted to. And that would give me 4 plus 2x to the negative 2 minus 2x to the negative 3. All right, remember your fractional, when you have exponents, you subtract the numerator minus the denominator, and that gives you the power on the variable when written in the numerator. So 2 minus 4 gives me negative 2, 1 minus 4 gives me negative 3 for the power. All right. Now, the question is, could I have done that from the beginning? And the answer is, yes, I could have. So 4x cubed minus 2x plus 1 over x squared. What was it again? Minus 2x plus 1. And this is my h of x. I could have reduced it from the beginning and written it as 4x cubed over x squared minus 2x over x squared plus 1 over x squared, which would reduce to 4x minus 2x to the negative 1 plus x to the negative 2. Right? Once I have it in that form, I can still take the derivative using the power rule. Even though the powers are negative, it still works. So I can do h prime of x is going to be the derivative of 4x, which is 4, times the derivative of negative 2x to the negative 1. The negative 1 multiplies by the negative 2 and gives me a plus 2. And then when I subtract 1 from negative 1, I get a negative 2. All right. Then pull the negative 2 to the front, and then subtract 1 and you get a negative 3. And notice you get the same result. Now, why don't we just teach this rule? Well, because most quotients are not single term polynomials in the denominator. All right. Most of them have addition and subtraction in the denominator, in which case you have to use the quotient rule. There's no other way around it. Right? Okay, I'm going to skip example 15 and 16 because I think we've done enough like those, and I'm going to go to example 17. If we have time, we'll come back to 15. It's kind of a difficult one and not the most important, so I'm going to skip it for now. I want to look at 17, which is an application. We have the population in millions of Arctic flounder in the Atlantic Ocean, modeled by the equation P of T, where T is time in the years, equal to 8T plus 3 divided by the quantity 0.2 T squared plus 1. Now, this is probably a real model. This is a real function, and we want to determine the initial flounder population. When they talk about the initial population, they're typically talking about time equals 0. In other words, the moment when you start the study, right, where nothing's happened yet. So time is 0 because no time has passed. So if T is equal to 0 for part A, what we want to do is find P of 0, which is going to give me 8 times 0 plus 3 over 0.2 times 0 squared plus 1, which is 3. So this is basically 3 million. All right. So at the time of this study, when they started it, there were 3 million Arctic flounder in the Atlantic Ocean. All right. Now we want to see how many there are at 10 years later. And then we want to also see what the rate of change is in 10 years. So 10 years later, P of 10 would represent how many flounder there are in 10 years. Oops, I lost the word many. So let's do that real fast. So in 10 years, P of 10 would give me 8 times 10 plus 3 over 0.2 times 10 squared plus 1. So this is going to give me 83 in the numerator. 10 squared is 100, and 0.2 of 100 is, I think, 20. So this gives me 21. So I have 83 over 21, which is basically 3.95. Now, if you just did this, you would think, okay, well, the number of flounder is going up, so everything is fine, right? It looks like it's healthy. That's not the only way to tell, though. What we want to do now is we want to find the rate of change in 10 years. So what is P prime of 10? How is it changing with respect to time? So now we need to have the difference quotient, which is going to give us this particular thing in the formula. Oops. I didn't leave enough space. All right. All right, so now we want to find part C, which is P prime of 10. So to find P prime, the first thing we're going to do is apply the difference, or not the difference quotient, but the derivative rules for the quotient, which is P prime of T, which is F prime G minus G prime F over G squared. Remember, the product rule, it has a plus. The quotient rule, it has a minus, right? So this is going to give me, the derivative of the numerator is 8 times the denominator, and then minus, the derivative of the denominator would be 0.4t times the numerator, which is 8t plus 3, all divided by the denominator squared, 0.2t squared plus 1 quantity squared, right? When you square the denominator, you square the whole thing as a group, not each individual term. So if we multiplied this out, we have derivative of the numerator times the denominator minus the denominator numerator. Just checking my work to make sure everything looks okay. So now I'm going to multiply it out. I get 1.6 t squared plus 8 minus, and now I'm going to work above, which is going to give me a 3.2 t squared minus 1.2 t, or plus 1.2 t. And then I change the sign, so it becomes minus 3.2 t squared minus 1.2 t, all over the denominator squared. And I'll teach you a trick, which is just to write g squared until you're done. And then the next thing that I would do is combine my like terms, which is a negative 1.6 t squared minus 1.2 t plus 8, I think, all over 0.2 t squared plus 1 squared. That's the formula, and we want to know what the rate of change is in 10 years. We want to know if the flounder population is healthy or not. So now we're going to plug in 10 to our formula to find the slope of the tangent line at that point to see if it's healthy or not. It looked healthy from just the straight numbers. It looked like there were more flounder, so it looked like everything was fine, but we have to check and verify. When you're done with this, I believe you get negative 164 over 441. Can somebody interpret that for me? What does that mean? Is it a healthy environment or not a healthy environment? This is basically a negative 0.372 million per year. Is it healthy or not healthy?
Unhealthy. It's losing a population.
That is correct. If you just looked at the number of flounder in 10 years, there's more flounder, you'd think it's a healthy population. But the rate of change of the number of flounder per year is decreasing, which means that it's losing population, which means it's unhealthy. There's something wrong in the ecosystem. Okay.